Is Earth currently experiencing a geomagnetic excursion or even a full-blown magnetic field reversal? How can we tell whether this is or isn't happening? Let's take a look. Hi everyone, Geophysicist Stefan Burns here, and welcome to the Earth's Magnetic Mysteries series. On this channel, we discuss Earth's geophysical energies and notable geologic events, as well as solar activity, planetary resonances, cosmic forces, and so much more. Welcome. One of the most critical components for understanding whether we are in a geomagnetic field excursion right now, or perhaps even a full-blown field reversal, is knowing the location of the magnetic poles and how they are moving across time. Also their strength. But we see here that our magnetic pole in the northern hemisphere is there up in the Arctic Circle. It's not down here deep in Eurasia, getting close to the equator. So if that was the case, we would immediately know that we are in some sort of excursion or perhaps even a full-blown reversal. The fact that it's not gives us a little bit of pause. Here we see the location for 2025 based on the 2025 World Magnetic Model, and we see that predicted location going all the way out to 2030. Based on that model, we see that that average movement per year is 34.5 kilometers. This entire distance is 175 kilometers approximately. And we see that just over the past couple of decades, it used to be moving quite a bit faster, 58.1 kilometers per year, going from 2007 to 2010. We can put in those modeled magnetic pole locations for 2020, 2015, 2010. You see that it was moving across larger distances during those 5-year time periods. It crossed over this ridge. Here, just for reference, is the Gokul supervolcano caldera from 1.1 million years ago. And if we put in our observed magnetic pole locations, we can see that it moved all the way over from Canada and now it's heading towards Siberia. You may be asking, why is it doing that? Is it a geomagnetic excursion that's occurring? Because this is quite a lot of movement in a fairly short time span. We go here, this is 1831, 1904. That velocity was only 0.76 kilometers per year, but then it really started to accelerate, especially around 1990. So if we put in our flux lobes for the northern hemisphere, then we can get a better sense of perhaps why it's moving. This is the dominant hypothesis at this moment in time. There is a flux lobe in the northern hemisphere in Canada, and then there's also a flux lobe over Siberia. Basically, the magnetic field in the northern hemisphere bifurcates into these two different flux lobes. And the flux lobe over Canada over the past 50 years has been getting weaker, and the flux lobe over Siberia has been getting stronger. And this is due to changes to the geodynamo and how magnetic flux moves through the mantle and magnetohydrodynamics and more. We have these sort of regular rhythms across time where there's changing flux across the globe, but we don't have a geomagnetic excursion or reversal. So we see that's moving here quite rapidly towards the Siberian flux lobe. And in fact, as it has gone closer to it, it has reduced in its velocity such that back from 2007 to 2010, it was moving 58.1 kilometers per year, and now it's only moving 34.5 kilometers per year, estimated 2025 to 2030. If we do look at its velocity from 2020 to 2025, it was 41.75 kilometers per year, going right there. And also we can look at something that's very important to be aware of, which is the actual location of the pole on the planet. Again, if we were in a geomagnetic excursion, then we could definitively say that if the pole was, let's say, down here or close to, let's say, the equator, or perhaps even already on the other side, right? But we are still well within the Arctic Circle for the magnetic pole in the northern hemisphere. In fact, it's quite close to the exact North Pole, which is quite interesting. So on that basis, we are nowhere near a geomagnetic excursion, but it has been moving fairly quickly. And this Arctic Circle flux lobe hypothesis is the best understanding that we have currently for why the magnetic pole in the northern hemisphere has been moving so rapidly and now why it is apparently slowing down. But it is a little bit of a different situation in the southern hemisphere. Let's check it out. And now we are looking at the Antarctic Circle here, and we see Antarctica, we also see New Zealand, we see Australia, and we see the location of the magnetic pole in the southern hemisphere, a positive polarity magnetic pole, an outward flowing field, and that location based on the 2025 World Magnetic Model is right there. And here we see how they expect that to move going all the way to 2030. That distance per year is 8.75 kilometers per year. So it's already about 1/4 the rate of change as it is in the northern hemisphere. But you will notice that it is already outside the Antarctic Circle. So that is already a little bit bizarre. We do have to keep in mind that we have some interesting dynamics at play in the southern hemisphere with the South Atlantic anomaly, and that is perhaps why this magnetic pole in the southern hemisphere is a little bit out of the Antarctic Circle and skewed away from that normal South Pole, North Pole axis, that tilt axis. But it's also not, again, like for example in Australia or near the equator. So it is still basically within range, you could say. And you will see that it actually used to be moving faster back in the past. So very much the opposite of the magnetic pole in the northern hemisphere. We put in those observed locations for just the recent past. For the southern hemisphere, we see them right here. And then we can also put in our model locations. And we see that it used to be on Antarctica itself back in 1903. You do have to take some of these measurements with a grain of salt because our equipment back then was not as precise as it is now, but they actually had boots on the ground. They were measuring it. This is what they got in 1903, and this is how they tracked it across time. And we see there that it took this sharp bend around the year 2000 and started to slow down, and it's especially coming to a crawl now in 2025. And so this magnetic pole is outside the Antarctic Circle, but again, it's not so far outside to immediately call into question, okay, are we in a geomagnetic excursion? Yes, we are, because again, it's not within these mid-latitude regions, which is where those magnetic poles will cross through before going to the other side. It's still, as you can see here, well south of 60 degrees. So it's north of 70, south of 60, just outside the Antarctic Circle, unlike the magnetic pole in the northern hemisphere, which is well within the Arctic Circle, in fact, very close to that perfect North Pole, but they are still very much well within range for the location of a magnetic pole for Earth's magnetic field on the whole. And now, keeping that in mind, we can turn our focus towards another identified very critical component for whether there will be a geomagnetic excursion or a geomagnetic field reversal, and that is Earth's magnetic field strength overall. We see that Earth's magnetic field strength has dropped about 5% per century since 1840, and that is when absolute intensity measurements were first developed by Gauss. And that approximates to about 12.5 nanotesla per year. And in fact, the dipole field strength has been decreasing at this rate since approximately 750 CE or AD. And so we have been going through a magnetic field strength decrease overall. But we have to keep in mind that these field strength values are relative to the geologic past across multiple time spans actually quite high. And if we look at Earth's magnetic field strength for the past 12,000 years or even for the past 900,000 years, we can see whether Earth's magnetic field strength right now is weak or strong relative to the historic past. And this is important because there has been a key level identified that makes a magnetic excursion or a reversal much more likely. The magnetic field has to reduce to a certain point. But first off, let's look at the past 12,000 years. We see this black line there is representative of Earth's magnetic field. And specifically, we're looking at a measurement right here for the dipole moment or down below the virtual axial dipole moment. This is not being measured in nanotesla. They have to reconstruct Earth's magnetic field strength based on geologic measurements or archaeointensity data. And so they use this VADM measurement, which is measured in amps per meter squared. So Earth's magnetic field approximately right now using this is 7.74 times 10 to the 22 amps per meter squared. And we see that across time, Earth's magnetic field strength has been lower and also higher than Earth's current magnetic field strength. For the past 12,000 years, this is about right in the middle, in fact. We see this period here from about 6,000 years ago to 3,000 years ago where Earth's magnetic field strength was lower. Also back here further in time, we also see some periods where Earth's magnetic field strength in general was greater, and we just reached a local high there about 1,200 years ago. We've been coming down from that since. But in general, Earth's magnetic field strength is not abnormally low like we see here at about 9,000 years ago or there about 11,000 years ago, where it actually got close to that critical value of 4 times 10 to the 22 amps per meter squared. Now, if we look at the past 900,000 years, we can see that in general, Earth's magnetic field strength right now is actually very strong on this time frame. We see that most of these values here are below the current value of 7.74. We do have some areas where it is higher, especially if you go back near that reversal time period right there. But all these arrows there denote a geomagnetic excursion. This one right here is the most recent excursion that has a lot of evidence behind it. This is the Lechamp excursion. There were others that have occurred since then, but they were weaker. There's not much evidence for them, just in general, not as notable of an excursion, whereas the Lechamp excursion about 42,000 years ago was a big geomagnetic excursion, nearly a full-blown reversal. We see that the magnetic field strength dropped quite a lot. Also back here dropped quite a lot about 100,000 years ago. So we see that we need the magnetic field strength in general to drop quite a lot for there to be a flip in the dipole, because you actually need the dipole to go away for it to then re-emerge on the other side. So it's not necessarily the movement of the magnetic poles across the globe and them changing positions. It's more so that the dipole field itself diminishes in strength such that it can re-emerge in the opposite polarity. Keep in mind that about 90% of Earth's magnetic field is made up of that dipole component, but you also have higher order poles, you have quadrupoles, you have octopoles. And based on the research, those stay a lot more static during a geomagnetic excursion and reversal than the dipole component. The dipole diminishes greatly, and then you have the dipole re-emerge on the other side. And with an excursion, it does not, you could say, cement or lock into place. So then the polarity goes back to where it was a few hundred or a few thousand years ago. And if we go back even further, 160 million years of time, we see that Earth's current magnetic field strength, denoted by this black line there, again 7.74 times 10 to the 22 amps per meter squared. That is quite a bit more than this historic record that we have. You have to take that with a grain of salt though, because we have limited data availability across this entire time frame. As you can see, quite a lot of gaps in the data. And also, as you go further back in geologic time, typically the resolution goes down and down. Your confidence decreases as well. But we can still look at this and understand that Earth's current magnetic field strength is quite high compared to the historic geologic record. And again, 4 times 10 to the 22 amps per meter squared for that VADM measurement. That is the apparent critical value of intensity at and below which excursions occur. We see that very clearly. The Lechamp excursion dropped us below that. The Blake excursion dropped us below that. The Jamaica Pringle Falls excursion dropped us below that. And then we see our last reversal there dropped us well below that field value. And again, we are at 7.74 right now. So Earth's magnetic field strength, in fact, is quite strong based on the recent geologic past, the past 12,000 years, also the past 900,000 years, and even the past 160 million years. But yes, it was stronger just about 1,000 years ago. Let's check it out. Right now, in the present moment, we have a very large magnetic anomaly of lower field strength hanging out near South America. But in the past, we had a big anomaly of positive magnetic field strength. And this is basically just because you had a magnetic flux lobe push out of the mantle and express itself with positive field strength, whereas you can also have that expressed with negative field strength, which is occurring right now with the South Atlantic anomaly. And so here we're looking at data out of Hawaii. We see this big increase in Earth's magnetic field strength there about 1,000 years ago. This is 1000 AD. Hawaii being a perfect place to measure these sort of changes because there's an active volcano there. It's always producing new lava flows. And if you can find those lava flows, date them, and record that remnant magnetization value, then you get a really clear understanding of Earth's magnetic field. And we see that Earth's magnetic field at Hawaii used to be about 65 microtesla there, or 65,000 nanotesla, whereas in the present moment it's closer to about 35 to 40,000 nanotesla. So we had this big pulse of increased magnetic field strength in Hawaii about 1,000 years ago. We also see that for France and in general for Western Europe around the same time period, though a little bit further back. We see that around 600 AD to 800 AD, we see that the magnetic field strength for France and in general for Western Europe was quite a lot higher, about 75 to 80,000 nanotesla in strength, and it's been decreasing since then with this 256-year periodicity stacked on top of that, this secular variation in Earth's magnetic field. And so these big changes in Earth's magnetic field strength going up or down are secular variations that sit on top of these larger trends like a geomagnetic excursion or a reversal, and they do not necessarily reflect the fact that we have a geomagnetic excursion happening right now at this moment in time. Just because Earth's magnetic field strength has decreased a bit since then does not mean that this is the total magnetic field strength decrease that is going to cause an excursion or reversal. it is a secular variation of a certain amplitude. And we also see large geomagnetic field anomalies for the Levantine Basin in and around Israel, for the Bronze Age to the Iron Age based on archaeointensity data. They've been making clay pots there forever, so we have really good data on Earth's magnetic field strength for the Levantine across time. And around 1000 BCE, there was a massive spike in the magnetic field strength in the Levantine Basin, and there was another one that followed around 750 BCE. So what we see across the globe are these magnetic field anomalies that occur. Sometimes they dramatically strengthen the magnetic field, sometimes they dramatically weaken the magnetic field, like the South American anomaly is doing right now at this moment in time. But again, these are secular variations and not necessarily 100% proof that there is a geomagnetic excursion that's occurring right now. They're probably related to them. When there is a whole bunch of negative field anomalies, perhaps that is when you get a geomagnetic excursion or reversal. Sometimes you get these positive geomagnetic anomalies where the field strength goes up and then subsides back down. And again, it's due to how flux lobes push out from the inner core through the mantle and then eventually out through the surface and dissipate into space. And if we compile the virtual axial dipole moment intensity curves for a few regions around the globe from 400 to 2000 AD, we see that they all experience these changing magnetic field strength anomalies at different points in time. So Western Europe and France were there around 800 AD, and then we see that Hawaii was more around 1000 AD, and then we see Mesoamerica had a really big increase in the magnetic field intensity around 1500 AD, whereas Japan has basically been trending with the overall axial dipole decline globally for this time frame. What have we learned here? Well, let's return to the question of, is Earth currently experiencing a geomagnetic excursion or perhaps even a full-blown geomagnetic reversal? Based on the geologic evidence, Earth's magnetic field strength needs to drop below a certain value for that excursion or reversal to take place. Effectively, the dipole strength needs to diminish so it can then re-emerge in the opposite polarity. And that lower magnetic field strength is being then carried by the quadrupole and the octupole and the higher order pole components of the magnetic field. So we see that with all the past excursions, Earth's magnetic field strength dropped quite a lot below a certain value. And right now, Earth's present magnetic field strength is nearly double that critical value of 4 times 10 to the 22 amps per meter squared. Whereas right now, Earth is at 7.74 times 10 to the 22 amps per meter squared. We also see with a geomagnetic excursion the movement of the magnetic poles across the surface of the globe, because as the dipole is reducing in strength, the surface expression of the magnetic pole starts to wander across the globe, and it does so quite quickly, and they eventually will swap locations. The magnetic pole in the northern hemisphere will pass through the equator and go to the southern hemisphere, and likewise the magnetic pole in the southern hemisphere will move north, pass through the equator, and then all of a sudden be in the northern hemisphere. And with an excursion, that attempted polarity flip does fail, and then the magnetic poles do then reverse their location and go back to where they used to be. And right now, again, if we look at the magnetic pole in the northern hemisphere, it is super close to the actual North Pole. It is nowhere near a zone on the planet that I would consider 100% guaranteed excursion territory. And then for the other magnetic pole in this dipole, the positive polarity one in the southern hemisphere, it is outside the Antarctic Circle. So it is a little skewed off that axis, much more so than the magnetic pole in the northern hemisphere. There is this asymmetry in that, which is a little bizarre. Though if we look at the other planets in the solar system, it's not that bizarre. For example, the dipole field of Neptune and Uranus is highly skewed off of its rotation axis. So there is some solar system precedent there, but we see that it's moving quite slowly as compared to the other magnetic pole. And it's kind of just going laterally along this Antarctic Circle there. It's not charging really quickly northwards. So I don't think we're in a geomagnetic excursion right now, or if we are, it's at the very, very, very beginning stages, and it's simply too early to tell. And I don't think we'll be able to tell whether that's going to be the case in our lifetime if we are in a geomagnetic excursion, because these things take hundreds to thousands of years to play out. But if we see the magnetic pole in the northern hemisphere all of a sudden pretty far deep here into Siberia and even perhaps into China or other areas nearby, and if we see all of a sudden this magnetic pole in the southern hemisphere get really close to Australia or move, closer to the Tropic of Capricorn, then we can say we are in a geomagnetic excursion with full confidence and not have that be some troubling topic. It's just the reality of the situation. But as of right now, Earth's magnetic field is strong, about 2 times stronger than that critical threshold needed to cause a magnetic field excursion as identified with the geologic data. And these magnetic poles are still basically in normal positions. Thanks so much for watching, everyone. You can continue your education into Earth's magnetic field by clicking the video on the left, or check out all the videos in the series by tapping the playlist to the right. Again, I've been your host, Stefan Burns. I'll see you all very soon.